Okay, then I shall start. And I want to point out that, S.A.G.E. this short course has gone through many iterations. And at one point, somebody said, why don't you leave all the theory to the end? Which I did, but then slowly, a lot of the theory I thought was necessary during the beginning. And so there's a lot of repetition here. Some slides have gone back to the beginning as well. So we will repeat certain things. On the other hand, that'll give me time to go through how we get the posterior probability that of the somebody's genotype in a pedigree, and also what we meant by the, what did we call them? The individual specific penetrance files, penetrances. Okay, so let us start. Oh, somebody else came. All right. Wait a minute. So we're going to start with familial correlations. And, oh, I can do this. And talk about the standard errors, which we've already talked a little bit about. But the whole point is that these standard errors make no assumptions about the distribution of the correlations. It uses what is known as the delta method to obtain the variance. And then the square root of the variance is basically standard error. So, well, I've just said that. Okay. But note, and this is the important thing, that when we have nuclear families, for example, the variance of the parent-offspring correlation depends on the mother-father covariance and on the sibling covariance. In general, whatever correlation we're looking at, it does require other correlations, which may or may not be estimable from the data, and maybe they're estimable, but only from 3 pairs. So we might want to know that. Oh, I've got to get over here. Excuse me. Where's this gone? Oh, so calculating the correlation. Okay. So we consider, and I think I went through this before, but I'm going to repeat it. We consider a collection of n pairs of observations as a set of random 2-element vectors, x, y, where the xi, yi going from 1 up to n. These vectors are not necessarily assumed to be independent, that's the whole point, or uncorrelated. But the structure of the pairwise correlations among them is known via the pedigree structure. So the pedigree correlation between 2 random variables, xi and yi, is estimated as a weighted, as you can see this, it's a weighted correlation. If you made the weights equal to 1, that would be just simply the ordinary Pearson correlation. So how do we choose weights? As we stated on day 2, there are different pairs, there's different weights you might use. If they were independent, and we might give the same weight regardless of pedigree size, and that would make the weights all equal to 1. Or we can make each pedigree has equal weight. Each pair of a particular type or subtype in the ith pedigree has weight inversely proportional to p, the number of pairs of that type in the pedigree. So the best weighted average that we obtain in S.A.G.E, if you use the latest versions, which, as you saw on, I think, day 1, what you have to do is to go back and use it's not in the GUI, so you have to go back and use the, you have to edit your parameter file, is obtained using quadratic models for the estimates of the variances. And what we mean by best is that we get the right coverage. So if we're asking for a 95% interval, we get a 95% interval using the usual method of taking the plus or minus, say, 2 standard errors. But it also assumes that to get this, we first of all transform the correlation using Fisher's Z transform, which very much normalizes the correlation. If the correlation is 0.5, then the distribution is automatically roughly normally distributed as a sample gets bigger. But if it's away from 0.5, you get a very skewed distribution, and Fisher's Z transform normalizes it. So we use the quadratic models, and you'd have to look at the paper to see how. We think they're pretty good, but whenever you use simulation, that means that the results only apply to the situations that were simulated. However, we simulated different pedigrees, different sizes, and we think, I say we think, that we've got a pretty good answer at the end in general. Now, we talked about testing for homogeneity among the K subtypes when you have P traits. And what you have to know is that for an interclass correlation, there are P-squared correlations per subtype. Remember, subtype is determined by the sexes of the individuals. So we test homogeneity among subtypes using a chi-square with K minus 1 times P-squared degrees of freedom. And what we showed you some results that gave you some chi-squareds and gave you degrees of freedom, but never told you how we obtained those. So this is the important thing. For an intra-class correlation, there are P times P plus 1 divided by 2 correlations per subtype. And we test the homogeneity among the subtypes using a chi-squared with K minus 1 times P plus 1, all divided by 2 degrees of freedom. And if you go back to day 1, you will see, for the example, the degrees of freedom follow these formulae. So among subtypes, for example, let's consider siblings univariate. So the statistics are Wald type statistics, and doesn't rely on maximum likelihood theory. Okay, it does assume you have normality, which you do eventually, asymptotically, and the fact that you do get this normality asymptotically is known as Slutsky's theorem. So there are 3 subtypes of sibling correlations. We test their equality by a statistic that follows a chi-square distribution with 2 degrees of freedom asymptotically if all 3 are the same. The test uses the fact that asymptotically all sums of squares and sums of cross products are normally distributed. What's asymptotic? That's a good question. I would say if you have less than 20 pairs to estimate a correlation, you might want to worry just a little bit. So this test cannot be performed if any of the necessary variances or covariances are not estimable. And so you therefore have various options within the program. Now I want to talk about maximizing likelihoods. Just about everything else in S.A.G.E maximizes likelihoods. So we need to know a little bit about maximizing likelihoods. Here is the basic theory for you. Consider one parameter now, just one parameter, theta, and everything can be extended to a vector parameter, theta. But right now, just for simplicity, consider one parameter. A maximum likelihood estimate, theta hat, of theta is a value of theta that there's two definitions. One, it maximizes the likelihood, and two, makes the likelihood largest within the parameter space. Now, if you make it largest within the parameter space, it may not be at a local maximum, but those are two different definitions people use, and you have to realize that. For example, in this example here, we're looking at the likelihood as a function, let's say, of a recombination fraction. Now, by definition one, the recombination, the estimate of theta is theta star, where the maximum is. But if we say, hey, the recombination fraction can't be greater than 0.5, then by definition two, the maximum likelihood estimate is 0.5. And in fact, the recombination fraction, as you know, has to lie between 0 and 0.5. All right, so it's important to realize that within S.A.G.E, we take definition two most of the time, and that leads to some problems, which we try and take care of. So consider this particular example, this funny likelihood. By definition one, theta hat, there are two maximum likelihood estimates. One at theta dagger on the left, and also one at theta star, because there are two maxima. On the other, I don't know what's wrong with my computer. Anyway, the recombination fraction, the likelihood is often undefined for theta less than 0. Let's see, that's about where we were, right? I'm sorry, maximum likelihood. All right. Under both definitions, maximum likelihood estimates enjoy the property of invariance. So the maximum likelihood of a function of theta is the function of the maximum likelihood estimate theta for any one-to-one function. Okay. Under definition one, and not necessarily under definition two, the maximum likelihood estimate has the following asymptotic properties. First of all, it's asymptotically unbiased, asymptotically efficient, and normally distributed with mean theta and the variance 1 over the expected value of the second derivative. Now, the point is that the likelihood is likely the function of theta in the data, and the expectation is taken over the data, i.e. over the random variables of which this is a particular outcome. Whoops, we're going the wrong way. Sorry. So in large samples, the expected value of the second derivative is the same as the second derivative itself, asymptotically, okay? And the expected information is the expected, but the observed uses the second derivative of the log likelihood. And what we do in S.A.G.E, we always use the second derivative of the log likelihood, and if you invert that, you get the variance. Now, of course, the variance is unknown. It's a function of theta, so we stick in the maximum likelihood estimate, and we get the estimated variance. Okay, so if you get an infinite standard error, that indicates very little information is available to estimate the parameter. When estimating more than one parameter, the likelihood may be virtually flat in some dimensions, which tends to happen whenever an over-parameterized model is used for the data at hand. For example, suppose we fit a model with 3 codominant alleles, but in fact one genotype does not occur in the data, say the A doesn't, then the probability of psi-AA in the population is difficult to estimate without Hardy-Weinberg equilibrium being assumed. And the transmission probability of this individual, the A transmitting an A, is difficult to estimate. Also, the mean is difficult to estimate unless you assume it's equal to the heterozygote mean. And also the variance is difficult unless you assume it to equal the variance of, say, one of the other means. Transforming data, we've been through, I can go through some of this fast because we've been through it before. For continuous data, we choose the hypothesis and transformation gives the best likelihood, but the likelihoods we compare must always be for the same data. And so this, you have to multiply this. We went through this before by the Jacobian, and S.A.G.E does all this for you. So the Box and Cox transformation, that tries to induce a normality of the residuals, conditional on type, or genotype if you're looking at genotypes. And we've seen all this before, so I'll just hurry through it. So the TI is the analysis trait, and typically lambda 2 is fixed, and we got to understand that theoretically TI cannot be normally distributed if lambda 1 is less than 0. It just cannot happen. So the purpose of the George and Elson transform is to induce to normality of the residuals in S.A.G.E. And we've been through all this before, so I'm going to rush through it now. We don't have to worry about it. Okay. Now, this is the bit I want to talk to you about. Pedigree likelihood and genotype classification of individuals. This is the stuff that I'm going to talk about after reading the Elston Stewart paper again carefully and deciding what's going on in my mind. First of all, we need some notation. Let P the probability, mass or density, Y the phenotype, U a major genotype, or more generally, remember, a major type, but under a genetic model, it is a major genotype. Psi U the population frequency of genotype U, and the P, this P value is the probability an offspring has genotype UI, given the father has genotype UFI and the mother has genotype UMI. And we are assuming we have a homogeneous sample. So in these slides we're going to do for the next few slides, we assume all parameters are known, but in practice we substitute maximum likelihood estimates from a large sample. So the likelihood for a Mendelian genetic model with 3 genotypes is this L, which is a summation. You can see it's a summation, and the psi U, the probability of U is a psi for founders, population genotype probability, and the others are the probability that an offspring from the father UF and mother UM have genotype UI. Okay, I'll just for you to understand that I wasn't clever enough to write it in this form years and years ago, so that's why I gave the method of calculating the likelihood, which turns out to be, interestingly, much faster than doing it this way, and I didn't even realize that was going to happen. But this is the way other people were looking at it. And I'll talk a bit more about that in a minute. So we use the fact that the likelihood of a parameter given the data is proportional to the probability of the data given the likelihood. So we define an indicator variables. An indicator variable, this looks like I'm not sure what version this is, but I did correct it once. So IWGI is 1 if person W has genotype GI. And in this case, we're assuming J goes from 1 to 3, 1, 2, and 3, because we're assuming 3 genotypes. Then the probability of the data given W has the genotype GI is this. What we're doing here, you take all this and you put it in here, okay? but you multiply it by this indicator. So it picks out those with, for individual W and genotype GJ. And then what you do now is you sum over those for the three genotypes. So you end up for individual W, what the probability is of genotype 1, 2, and 3. Now remember, this is important. Normally we have a posterior probability is equal to a prior times the likelihood given that the prior hypothesis, given the hypothesis. We have to do this. Remember, this is what we always do. We have a prior hypothesis, and then we gather data, multiply that by the probability of the data given the hypothesis, and that gives us the posterior. Okay, this is the real problem. What do we assume about the prior that W has genotype GJ? What can we do about it? I mean, it doesn't make sense to say, well, let all the priors be equal. I mean, where could that come from? But you have to have a prior. So this is the neat trick we do. We suppose there are W individuals in a pedigree, and this is expanding what's at the end of the Elson-Stewart paper. We consider all the possible assignments of the 3 genotypes to these W individuals. In other words, there are 3 to the power W possible assignments. And then we assume that a priori, these 3 to the W assignments are equiprobable. So let J be the likelihood for one of these assignments. Then the probability W has genotype GJ for J 1 to 3 is given by this. We sum these and we multiply by those we pick out here the ones we're interested in, the particular W and a particular GI, and then we divide by the sum of those, the GI. And so this is the probability W has genotype GJ on the assumption that the assignments are equiprobable. And this seems to me to be pretty reasonable. I mean, why would they not be, all the possible assignments? So now let us consider again what we had before, which this is no prior assumption based on the data alone. Okay, and this is what we decided. We were talking about this, and since now I know this was done in New Orleans because Alexa said she programmed it, and Joan, I think it was Alec who said, why can't we use these as penetrance functions in linkage analysis? And I must have agreed. So whenever Segreg has defined a model with Mendelian segregation at the locus, these probabilities, as well as the probabilities a person has W has genotype GJ, are available in the type file and can be used as what we called individual specific penetrance functions for linkage analysis. So that's the history of it. And I see no reason why it can't be done. I mean, it can be done.
Can I interrupt with a little correction?
Sure, please do.
When I said I remembered programming that, I actually went back and looked at the code, and I saw that what was written out in the file was just the probability of each genotype, not the other little bits on the way to, to computing it. So in other words, this was computed, but the parts, it didn't write out the things that you're calling individual specific penetrance functions. It computed them, it just didn't write them out. So Kevin probably had the idea to include those parts as well.
Wasn't it Jeff?
Oh, you mean that what you were saying is, what I say is probably correct for the current program. Is that what you're saying, Alexa?
Well, it probably is, but the old program did all the same computations, I think. I mean, and it had like 3 different ways of estimating the penetrance, but it just didn't write all the parts out that are currently written out.
Right. You're saying, what you're saying is these individual penetrance things, these individual specific penetrances weren't there.
They
right?
weren't written out. They were computed as part of getting the genotype probabilities. They just weren't written out.
In other words, in the type file, there was only 3 probabilities, not 6 as currently. Is that what you're saying?
I think I can probably may help that. I believe the type probability file was added by Jeff Weddick.
Okay.
Well, I did write out a type probability file. It just didn't have as much in it as the current one does.
Right. Yeah.
Right.
Yeah.
Written by Jeff.
Right.
Yeah. When we were there, it was just, as Alexa said, the type probability file was just based on the genotypes. Yeah. And then
Okay.
the additional bit, which is really cool stuff, was added once you went to case.
Okay.
Yeah.
But so
It's been too many years, all this
I know.
development over the years. It's exciting, though. It really is. Things keep getting better.
As I said, there's so much in this. What I don't know is I suspect that what is added is when we're trying to get the probability that an individual, for an individual, what's his posterior probability of having a particular genotype. I suspect that is based on, because you could 3 to the W is a W, what was it? 3 to the W can be a huge number. I suspect it was just based on a random sample of 100 individuals. Okay, to get the posterior probability that somebody has a particular genotype. That's my guess. I don't know. It would be better if this were, if somehow you could let it choose the right number to get something accurate.
Can I ask a question about that?
Yeah.
Those equiprobable
assignments. Yeah.
It seems to me that you wouldn't consider as many as 3 to the W because of assumptions about parent offspring. In other words, some combinations of parent offspring genotypes would not be among the possible.
Yeah, but then don't forget, this is you're now at a genetic model, so they would have likelihood 0 anyway. Okay.
Okay.
This is done. So you've got to understand, this is once you've got a genetic model. So those likelihoods you're worried about are 0 anyway.
Okay.
Okay.
Yep.
Yeah. Okay, good. Well, I'm glad I got that straight. All right. So let's consider regressive models for continuous traits. And I got to watch the time. We go on till 11. Okay, we're good. So now we'll look at more general notation. P as before, probability, mass, or density. Y is the phenotype. U is the major genotype, or more generally major type. And now we have a polygenotype, capital G, it's continuous. And we have a probability, prior probability for population frequency U. And then we have this, again, this transition probability, but we also have one for the G's. That's, you have to realize you have this, probability that an offspring is GI given the father is GFI and the mother is GMI. And now we will define this. This is the ordinate of a normally distributed random variable with ordinate Z of a normally distributed random variable with mean 0, if you like, and variance W. Okay. So what's the likelihood for a random pedigree? So this shows you before what I didn't understand. You can write, if you know the genotypes, you can write it simply as the probability of PU times the penetrance function of property of Y given you. And then since you don't know them, you summation over the three, well, there's many types as you want for each individual. And I say lots of people were doing this and I didn't know it. I didn't understand what they were doing. Hence the Elston-Stewart algorithm just by accident. Now in the mixed and unified models, what you have is the same kind of thing, but now not only do you have to sum, but you have to integrate over the polygenotypes, okay? And the Elston-Stewart algorithm is not possible in this case, except by approximation. So consider the transmission probabilities. This is a transition probability. These are the transmissions. They're all the probability of a particular individual transmitting capital A. They're the transmission probabilities. And basically, what we would like to do, I mean, we'd like to estimate all these and see if they fit Mendelian inheritance. Well, this is a way of making sure you don't have to estimate all these. We just estimate these because these are a function of these. And we're going to ask now, do we get Mendelian transmission? So for two alleles at one autosomal locus, there are 12 functionally independent ones of these because there are 6 mating types, 3 probabilities of each that sum to 1. So it's 6 3 is 18 minus 6 is 12. Okay. So the transmission probability model is like this. It says the probability of, let's suppose we have just two alleles. The probability of this given the parents is the probability the father transmits an A and the mother transmits an A. We're assuming just 2 alleles, A and B. So the probability, let's do this one, B is this is the probability that B transmits an A. It's going to be 1 minus the probability of an A being transmitted. And similarly for the second allele here, you've got the probability that an AB transmits, the probability of AB given the father's thus is you've got the transmitting an A and not transmitting an A or B, plus the other way round. The other way round because it can either be, you can think of this, what's the father and mother contributing. So now to have homogeneity across generations, you have to, these 3 probabilities have to be the same as the original probabilities. And that means you have to have Hardy-Weinberg proportions, and it turns out you have to have this constraint as well. That's the point. So note that Hardy-Weinberg equilibrium is no restraint if you have dominance or recessiveness, okay? But you do have to have this restraint. That leads to complications. So when you look at the segregation analysis test statistic used by S.A.G.E, this is what you get. Remember, we are assuming as a model a column, and under that model we are testing a hypothesis. So here, if we test if under this homogeneous but no transmission model, if we test that it's homogeneous general, if I got it right, we're testing this under have I got it wrong way around? I can't remember. Hold on. Yeah. You get a chi-squared with 2 degrees of freedom. And in this case, 2T is a 2-type model, 3T is a 3-type model with Hardy-Weinberg equilibrium, and then 3T NWH. We can't have that here because it's homogeneous. That's a 3-type model without Hardy-Weinberg equilibrium proportions. So you notice some of these, they turn out to be chi-squareds. Here you see here, here, and here, asymptotically. The reason that this is a mixture of chi-squareds is because you are on a bound. You're on a the null hypothesis is on a boundary of the model, and this one as well. These days, I mean, when we first started, there were very little literature on what happened. Nowadays, you can see various. You can find quite a lot of literature on what you do at bounds, and I recall that the paper came out by a guy called Stephen Self, and I can't find anything about his publications. He doesn't seem to exist anymore, hardly, but he came out with this beautiful theory of what to do on bounds. He's the first person that I know of that did that. Okay. So let's just consider a nuclear family, make life easy, on each member of which you have a continuous phenotype. So let this bold Y indicate all the Ys we have. We have the father's phenotype, the mother's phenotype, the first child, the second child, and the last child. And let's assume this follows a multivariate normal distribution with no major gene first. Okay, so you get this. This is normal theory, where the this n over 2 is because you have C plus n is C plus 2, the number of individuals in this family. The expectation of the Y's is the same, mu, because we're now just assuming this is true when there's no major gene and we have a common variance. Okay. And the variance covariance matrix, here's the mean vector that goes into here. Here's the variance covariance matrix. And typically we're going to allow for a father-mother or spouse correlation, a parent-offspring correlation, and a SIB-SIB correlation, and variances all down the diagonal. So these are the correlations we're going to allow for in this. At this point, though, there's only one mean. So now we decompose this. This is the density of a vector of Y. We decompose it. First of all, we have that it's equal to the probability density or probability density of father, mother given the father, first child given the father and the mother, second child given the father and mother and the first child, and so on. Okay, right up until you get the last child given all the rest in the family. It's a product of C plus 2 univariate normal densities. So this is what we've done now. We've decomposed the multivariate one into C plus 2 univariate normal densities. i.e., we now have it in the form we product over the father, mother, and all the kids from 1 to C. And this is a normal density where Zi is an adjusted value. It's adjusted for all the previous ones. And Wj is a continuous conditional variance. Whatever's this? I don't want that. Get away. All right. So father is normally distributed with mean mu sigma squared. And there it is, there. So the conditional that we know the mean, the Z, that what is normally distributed with mean 1 and variance sigma squared is ZF. This has, if you like, this has mean 0. It's the ordinate at that point. And the conditional variance, well, it's the ordinary variance, sigma squared. That's for the father. Now let's look at the mother given the father. Well, what we find is the conditional mean is as before, but we now have to multiply. The conditional mean is this plus beta, which in this case is going to be the correlation coefficient between father and mother of this mean corrected father one. Conditional variance is this, and you have to take away, it's 1 minus the correlation squared for the correlation in mother and father. So we now write the one for the mother. What we take is the mother's minus the mean minus the correction for the father, regression on the father. And here we had the residual variance, what's left over, the variance after you've allowed for the fact that you're conditioning on the mother, on the, yes, mother. So what we can write is we write this normal, this thing that's going to have mean 0 as all this, where in this particular case, the regression is the same as the correlation, and the residual variance is the original variance for the father minus it times the correlation with father and mother squared. All right. Look at the first child. We end up with this. Okay. This is the conditional mean. We have to take away, this is the mean corrected father's value, mean corrected mother's value. And for the first child, this is what we do. And so we write our Z's. We did this, we did this, we did this. So now let us suppose each individual has a particular major genotype. All right, then we can still write the likelihood as a product of C plus 2 normal densities if we define the way we've just done, etc. Okay. So the regressive model likelihood for the nuclear family is just this. And the point is we could write it this, and it turns out that, whoops. Oh, excuse me a minute. All right. You notice there's a nested summation here, and that's necessary after the product sign here because of the dependence amongst the SIBs. So if we could write it this way, with just this simple way like this, then the calculations would follow the same form as the Elson-Stewart algorithm, the same number of summations, and therefore relatively fast. This can be done in various ways. For example, you can use a class A model, or you can use an approximation. I'll say a little bit more what that approximation is. So in the class D, come back. In the class D, an individual's phenotype depends on ancestor phenotypes only through his/her genotype and the parents or SIBs phenotypes. In the class A, we only use the first 4 terms. Up to this one here, we use 1, 2, 3. Wait a minute, up to this one. Excuse me. Whoops. I'll be back in 1 minute with you. Up to this one here, we got 1, 2, 3. For some reason I've got 4. We go up to that one, 3 terms. I'm sorry. I miscounted yesterday. The approximation is this peculiar thing. For all j less than I, we do this. It's a very peculiar approximation. It's due to Sandra Hastert, and it seems to work remarkably well. Don't ask me why. I don't know. So transformation, we can segregate, you can transform both sides. And when calculating the penetrance function for every individual, you just have this replacing this. If we have a composite trait, then this replaces the y plus minus mu I. You've got all this stuff in here as well. Okay. The parameter estimates, other than the variances, are median unbiased on the original scale of measurement. Now, you don't have to transform both sides, as we'll see later on. And if you don't, then you will get mean unbiased estimates. But it's my belief that median unbiased estimates are more interesting. I hate to get mean unbiased if there are any outliers anywhere. So the variances are on the transform scale, and Karen Rupert shows that you're getting median unbiased estimates. Okay, what time is it? And we're only 7 minutes late after all that. I apologize for all the, before we break, any particular questions at this point? No? Okay. So what we will do is we will break for, let's say, till 11:15, okay? 11:15, as in 7 minutes time. Then we'll come back. And I will not touch this thing.